So I would like to give a short summary of the key scientific findings of this fifth assessment report of Working Group 1 of IPCC. The report has been produced over the last roughly 5 years, so started the process sometimes in 2008, then ended with the approval plenary of the summary for policymakers in Stockholm in September 2013. If you haven't heard of IPCC reports yet, these reports are mandated by the governments of the world, but they're obviously conducted by scientists and by actually a pretty large number of scientists. Thank you very much. So this is the image of the cover page of our report. It shows a Norwegian glacier, and the image has been chosen because it nicely connects different components of the climate system: atmosphere with clouds, water vapor. It also has the Arctic in it. It has glaciers, and this glacier goes into the ocean. So it nicely connects these components of the physical climate system that this report is mainly about. I'd also like to acknowledge the fact that I'm not standing here on my behalf. I'm on behalf of 259 authors who have contributed to the entire report, authors from over 30 countries of the world, and also the team in Bern, the co-chairs of the Working Group 1 of IPCC, as well as the technical support unit team. A short summary, as I started off, 2009 the process started where scientists had to put together an outline, how they see this report to shape up in an IPCC process, in this intergovernmental process. The governments are involved in shaping the report because they ask for this report and they want to see certain questions answered or at least discussed. And therefore, the outline goes through an approval process where the scientists put it together, and then sometime after, a couple of months after, the governments actually approve the outline of the entire report. Then in 2010, authors that are writing the report are nominated and selected. This also involves governments. The governments nominate their experts. For example, Finland has nominated experts from this field, physical climate change, and in the end, 2 authors or 2 experts have been involved. Timo Vesala, who's here as a review editor, and Veli-Matti Kerminen as a lead author on the clouds and aerosols chapters. The process that these reports undergo is rather strictly organized. It's a multi-step review process. The experts write first a zero-order draft, which is kind of an internal draft, just to see how the whole report steps up, basically just putting in what individual authors contributing think should be covered as part of the approved outline. And then it goes through 2 steps of formal review. Formal review means it is made available to experts worldwide and to governments for review. Through that process, experts and governments can provide review comments, similar to peer review process. The difference is that every and each individual of these review comments needs to be addressed, it needs to be responded to, and the 54,677 review comments that we've received from over 1,000 experts will be made public, including the responses at the time of the launch of the report, which happens to be 30th of January 2014, so only a few days from now. The Working Group 1 report consists of 14 chapters. It's over 1 million words. That's not of much use for policymakers trying to use that information to come to conclusions and make decisions. Therefore, the entire report is being condensed first into a technical summary of about 100 pages, 50, 60,000 words, and then into a summary for policymakers, which is a document that I have here in one example. It can be downloaded from the web. It's a 30-page document with the key conclusions and explanations included, about 14,000 words. This summary for policymakers for the first time in the IPCC, what Working Group 1 co-chairs and the authors have tried to do is take these 14,000 words and actually condense them even further. So we've come up with 19 headline or key messages from that SPM, which can be put on 2 pages, which it seems have been widely appreciated by the policymakers and other users of the report over the last roughly 4 months since the report has been published. Now, as I said, it's the Intergovernmental Panel on Climate Change that writes this report, but of course a panel doesn't write reports, so it's really these individual scientists that have produced the report, which also put the face on these over 1 million words and 14 chapters. And I think it should be thanked, these people and the organizations that nominate and fund them to do that very much. So it's not, I mean, they're all dedicating their time and efforts to produce the best possible assessment of the current status of climate change science. 209 lead authors, 50 review editors from 39 countries. In addition to these individuals that I've depicted here, there are over 600 contributing authors, which are also named on each of the chapters as contributing data, contributing figures, perhaps even contributing text, who have also made contributions to the overall report. So it's a large number of individuals. It's an effort of the entire community of physical science that leads to such a report. Now, I thought it might be good to put the Working Group 1 report and IPCC a little bit into context. This is the structure of the IPCC. Its host organizations are WMO and UNEP. The governments that are part of WMO and UNEP also make up the IPCC plenary. So that's a government body. And a part of that plenary is then kind of the executive board, which is the bureau of IPCC. Important part is there is also a secretariat of IPCC, and the secretariat is the only permanent part of IPCC. It's about 10 people working in Geneva, which are permanent, and all other parts of the IPCC are basically temporarily built up for producing such a report. And once the report, our Working 1 report is done, the technical support units and the authors kind of go back to their original work and are no longer involved or part of the IPCC. IPCC is not just one working group, despite the fact that I will focus on this Working Group 1, physical science basis. It also has a second working group on climate change impacts, adaptation, vulnerability. Then a third working group on mitigation of climate change, costs of climate change, scenarios and options and requirements to reach certain future scenarios. And then it has a task force on greenhouse gas inventories. And most importantly, it's really the scientific community that builds the basis and the fundament of the entire process. So it's not by no means kind of a gray body of bureaucrats that produces these reports. It's really a scientific community effort that in the end leads to 14 chapter report in the case of Working Group 1. Important, Working Group 2 will have its approval plenary in March 2014, and Working Group 3 will have the approval plenary in April 2014. And so by the end of 2014, the entire report, plus a synthesis of that report in the synthesis report, will have been published and made available to the public. Now, two things that are important for IPCC. The principles of IPCC state that the assessment has to be on a comprehensive, objective, open, and transparent basis. And that's, I think, one of the things that all the authors are really working on. We have this whole review process, and comprehensive means for Working Group 1, it's over 9,200 peer-reviewed papers that are cited in the report. This is not the literature that has been looked at. There was even more, but the ones that in the end made it into the report, it's over 9,000 scientific publications. Also, IPCC must be neutral with respect to policy. So whatever we do needs to be policy relevant, but we cannot be policy prescriptive. If there is anything that governments perceive as being policy prescriptive, they will raise their flag and they won't accept that language in, for example, a summary for policymakers. Now, very quickly the process, and most what I want to say here is that the governments are mandating, they're heavily involved, but it's basically working together to produce this report. And I've just briefly put on the timeline over the last 5 years to show the different steps of involvement of the scientific community, the selected lead authors, and the governments. And you see this whole process of developing an outline, approving the outline, nominating and selecting experts, involve governments. Then once this has happened, it's really the scientific community producing the underlying literature and the research, and the authors producing these drafts, which are the ones deciding on what the report will look like in the end. And governments have the possibility, like other experts, to comment on it, and in the end they accept. So it's really a close collaboration over 5 years, which really works well. And from the Working Group 1 approval plenary, where we went through the 14,000 words of this document, word by word, with 110 governments sitting in the room and basically being able to comment on each individual word, formulation, sentence, paragraph, figure. And there is no fundamental change in the key conclusions that we have. None of the key conclusions that we went into that plenary has been changed due to changes or requested changes by the governments. What it really happens is that the formulations sometimes put down by us scientists are probably still, while we try to be clear and concise, they're probably still too complicated for a policymaker. So often what happens is that the language gets really improved in a sense of understandability for a more general public outside of the scientific community. So with this, I really would like to go into the details of the Working Group 1 report of AR5. Just to highlight, it's not the first, it's the fifth. And if I had to summarize what is the key outcome of the fifth assessment report, I would say we didn't have to revise a single key statement from any of the previous reports due to new scientific knowledge. It's really, we now can confirm most, if not all, of the key conclusions from previous assessment reports, which gives us a lot of confidence in the robustness of the science that this working group has looked at. Now, I would like to structure the talk about the content of the fifth assessment report of Working Group 1 along 3 topics. One is observations, then into the understanding of the observed changes, and then go into the future, what we might expect, what scenarios are available, produced by economists, given to the physical science community, and what then the climate models tell us about the future. And so the question is, what has been observed? What has changed in the past? And let's start with atmospheric surface temperature. This is an image of the surface air temperature anomaly. So we compare the measured temperature to a 1961 to 1919 average and look at the evolution over time. And what you can see is that if you bin this into decadal averages, you see that there have been fluctuations over between 1850 up to 1950. There is ups and downs, variability, even if you look at decadal averages. But then the last 3 decades really go off, and the warming compared to the rest of the last 150 years is becoming evident. It's also important to mention that this is not one temperature record, but it includes 3 temperature records from independent organizations from 2 countries, which basically showed the same result. For simplicity, there's only one error bar or uncertainty bar plotted from the black measurement section. So one of the key conclusions in the Working Group 1 report is that looking at these records is that each of the last 3 decades has been successively warmer at the Earth's surface than any preceding decade since 1850. And this is independent of the last 15 years. It's just stating the long-term trend of temperature records at the surface, and this combines land and ocean surface temperature. Interesting is also to look at the longer-term context, not just the last 150 years, but also go back over a millennia or 2 millennia as much as possible from, for example, tree ring reconstructions. And for the Northern Hemisphere, these last 30 years, so 1983 to 2012, were likely the warmest 30-year period of the last 1400 years. And in IPCC language, you see we always try to qualify the uncertainty. So there are two qualifiers of uncertainty in that last sentence. One is likely. This means with a probability 66% to 100%, so larger than 66%. And there is a lot of, or still uncertainty about, for example, what exactly the medieval warm period did. So the scientists put kind of a qualifier of the confidence that they have in that particular statement and said, oh, but we only have medium confidence in this overall statement. So the first statement given here is a statement of fact. So scientists are willing to state that as a fact, whereas the second statement has these two qualifiers which indicate a sense or a measure of the uncertainty associated with that particular statement. And these likely and confident statements, you will see they will come in many different places of my presentation. Of course, it's not just instructive to look at the global mean temperature. Temperature is not felt globally, it's felt regionally. Everybody feels temperature changes. And if you take a map that shows the temperature change from 1901 to 2012, you see that almost the entire globe has warmed. If you look very carefully, you will see two things, except, you have one is the color bar. So you go to red, purple colors means warmer. Bluish colors would mean cooler, and there's only two regions where enough data is available where we see a cooling. One is over the North Atlantic, and one is here over Central North America. And if you also look carefully, you see that the map has these black crosses on top, and the black crosses give an indication of how certain or how well quantified the trend is that is given here. And the areas with a black cross are the ones where the scientists say there is high confidence that the number of the trend that we give is correct, whereas for the areas where there is no crosses, the uncertainty is much bigger. So exactly those regions where a cooling trend has happened, the scientists say that the trend that we observe is not far enough outside of the natural variability of the system to say that there actually has been a significant trend. So it's a test of significance of these changes. Large parts of the globe, you can also see that it's not yet possible to give a trend over 1901 to 2012 simply because of the lack of available data. Warming of the climate system is unequivocal. So there is no question that the system is warming. One piece of evidence is the temperature record, and this also the distribution of temperatures. But the highlighting of the temperature sometimes leads to the perception that it's actually just the temperature. But if you look at the precipitation map, which is also in the summary for policymakers, you see that even precipitation, this is the top one, is from 1901 to 2012, and this is from 1950, from 1951 to 2012. And you clearly see that you see two things. One is that the more you go to more recent decades, the amount of data that becomes available is bigger, and so we can actually calculate trends over more parts of the land surface. And you also see that many regions of the globe actually see quite substantial changes in precipitation over the last 50 years, in some areas also over the last 100 years. So also the hydrological cycle sees sustained changes over the past. Other changes that are observed or reconstructed from paleoclimate information are, for example, the CO2 concentration in air. We can do similar analysis for methane, for NTO that exists, has been published. This is all based on Antarctic ice cores, which happens to be one of the places they're being analyzed is the University of Bern. And important is that if you look at the CO2 concentration globally average. The 2013 value is outside the range of this natural fluctuation that we've seen over the last 800,000 years, including 8 glacial interglacial cycles of the Earth. So it's 40% higher than any time in the last 800,000 years. And in summary, the atmospheric concentrations of carbon dioxide, but also methane and nitrous oxide, have increased to levels which are unprecedented in at least the last 800,000 years. So really substantial changes in the composition of the atmosphere that have been observed. If you go away from land and atmosphere, now go to cryosphere, the ice sphere. And here is a plot of the cumulative ice loss since 1992. That's the time when satellite measurements became available, which are the only means to get good estimates of these trends in ice stored in glaciers or in ice caps over Greenland and Antarctica. And you see that the left axis in gigatons of ice and the right axis for instructive purposes in sea level equivalent. How much has that contributed to sea level over the past 20 years? And you see that all these three components, glaciers, Greenland, and Antarctica, they all show a loss of ice over the last 20 years. And important is, of course, there's quite some uncertainty in this statement. So by no means there is an exact measurement of how much ice has been lost from Antarctica or from Greenland. There's a large uncertainty, but that's always depicted in the plots that I will show you. Overall, the ice loss from glaciers per year, gigatons per year, about 226 gigatons per year loss from glaciers globally, 215 gigatons of ice lost from Greenland, and 147 gigatons per year lost from the Antarctic. So that's quite substantial changes in the total mass of ice that have been observed and have been published and reported on in the scientific literature. If we go one step further, we can also look at the hydrological cycle. You remember I've shown you the precipitation over land, but now over the last 20 years there has been a lot of progress in the scientific community also to look at changes over ocean. And because we don't have measurement stations of precipitation, scientists found a way to find an indirect way about precipitation changes and evaporation changes over the ocean, taking into account the salinity fields at the surface of the ocean. And you can see from the second map here that if you look at the trend in surface ocean salinity over the last 50 years, so 1950 to 2000, there have been quite substantial changes in the salinity distribution of the globe. The north, the Atlantic, has become more saline, so less fresh. The Pacific has also some indications of more saline parts in the subtropics of the southern hemisphere, some freshening in the northern hemisphere. And this kind of is an imprint of the loss of water from the ocean surface by evaporation and the gain of water of the ocean surface by precipitation. So it's an indirect measurement of the evaporation minus precipitation. And really these salinity fields and from the surface ocean salinity from ship measurements, but also from buoys that have been deployed, really provide very compelling indirect evidence that E minus P, so the hydrological cycle, has also changed substantially over the oceans. And this is a statement that is made with medium confidence in the report. If you go now into the ocean and how the ocean content has changed with regard to heat, there are a number of independent records that have tried to quantify the changes in ocean heat content over the last 50 years, where data is available in good quality. And what they all show is that if you compare it to 1960s, the heat content in the ocean has increased. There's a lot of fluctuation, there's a lot of natural variability on top of this trend, but there is a clear indication of the ocean heat content increasing over the last 50 years. So the statement in the summary for policymakers of the IPCC is that it's virtually certain, so probability of more than 99%, that the upper ocean, the top 700 meters, has warmed between 1971 to 2010, and that it is likely, so more than 66% probability the ocean warmed also between 700 and 2,000 meters from 1957 to 2009. The further back in time you go, the uncertainties become larger and larger. So it's really probably won't be able to go further back in time with regard to ocean heat content. But it will be very interesting to observe what will happen over the next decade or so in the ocean surface, but also in the deep ocean. Now you've seen all these changes in heat and precipitation in the hydrological cycles. I've tried to convince you that the changes are really happening, that they are observed. But if you go back and look at the most fundamental quantity that we can look at, energy, and now out of this composite of observed changes, try to make an energy budget of the Earth system over the last 30 years. And this is what we've tried to do here, bringing together all the information from all the different components, ice, atmosphere, ocean, land, into an energy budget. And what you see here is the cumulative energy budget over time. So if you follow the top of these colored lines, you see that the energy stored in the climate system has increased over these last 30 years by about 250 times 10 to the 21 joules. There is uncertainty, and this is indicated with these dashed dotted lines which apply to this top of the line. That's the total energy change in the climate system. We now have tried to separate this based on the different types of information into an ocean part, which is the blue, upper ocean light blue, deep ocean dark blue, into the ice component, so which part of that heat has gone into the cryosphere, into the land, warming of the surface, and then warming of the atmosphere. And if you follow the discussions a little bit in the public over the last 4 months, one of the biggest, or 4 months and longer, 2 years, the biggest discussion that we have is what happens to the warming in the atmosphere? And that's a very important and very interesting scientific question. But if you look at this in terms of an energy balance question, the atmosphere is a tiny fraction of the overall heating of the climate system. The conclusion from the report is that it's obvious that the ocean dominates the increase in the energy stored in the climate system. More than 90% of the extra energy goes into the ocean if we look at the time period 1971 to 2010, where we have high quality data available. Now, let's have a look at understanding these changes that I've reported from the IPCC report. Why have these changes happened? And that becomes a bit more tricky. We cannot measure why. We can try to compose, like in the energy budget, the sources from different information, put it together, so we can understand why the energy budget has changed looking at the different components. But the source of the changes, we need to go one step further, and that involves usually physical understanding, theoretical understanding, but also climate models and process models. So we now move out of this observed component of the climate system into where we have to combine models and observations to improve our understanding. And this is one very complicated graph that is also in the summary for policymakers. It's in the summary for policymakers because it's one that has a long tradition in IPCC reports. Policymakers really like to see that graph because it summarizes the different drivers of climate change in terms of radiative forcing in watts per meter square. And this graph, how complicated it might be, it's very simple. You have here a line that is the zero line. We look at the radiative forcing in watts per meter square since 1750, and you have a list of components that have a potential to change the energy flux at the top of the atmosphere, to change the climate. That goes from well-mixed greenhouse gases, CO2, methane, N2O, goes to short-lived gases and aerosols, gases that we know from air pollution, etc. Everything here is anthropogenic, and then we have natural sources of a natural source of an external source of changes in climate, which is the sun. And if you look at these plots, we have some positive bars So they lead to, the changes in these quantities lead to an increase in the energy flux at the top of the, lead to a warming in the end. And we have negative bars, which would lead to cooling. And the big negative one are NOx-related components, and mostly aerosols and aerosol and resulting cloud adjustments. But if you sum up the total anthropogenic contributions, so all these bars starting from here up, the total anthropogenic forcing compared to 1750 is positive, even if you take into account the quite substantial uncertainty. And what you also see is that individually, CO2 provides by far the largest forcing component of all components. And if you sum up all the greenhouse gases, the well-mixed greenhouse gases, they actually are larger than the total anthropogenic because of these negative counteracting effects from aerosols. What is also very instructive is to compare the total anthropogenic, the red bars, with the changes in solar irradiance. So the changes in the sun are much smaller than the changes by the anthropogenic drivers, mostly CO2. And that's what this bar tries to summarize. And if you go and just look at this one, and you see also that the forcing from anthropogenic factors, from anthropogenic drivers, has increased over the last 60 years quite substantially by about a factor of 3 to 4. So 1950, the forcing compared to 1750 was about 0.5 watts per meter square. It is now more than 2. In fact, it's 2.29 within an uncertainty bar that is given there. And this leads to the conclusion that the total radiative forcing is positive, and it has led to an uptake of energy in the climate system. The largest contribution, as you can see here, or could see in the plot before, is caused by the increase in atmospheric concentration of CO2 since 1750. It's also important that the sun plays a much minor role in that period since 1750. What is not in the plot is volcanoes. Volcanoes can have a very large forcing on a negative forcing because of the pumping out of aerosols into the stratosphere, but that's usually only lasting for a few years. And if you look at the time period 1750 to 2012, the net effect of volcanoes is considered to be small. Now, we have another component. It's not just the forcings, the external forcings that change, but it's also feedbacks within the climate system that have a potential to change the temperature, for example, of the atmosphere. So in addition to external drivers, which tend to warm the system, as I've shown you before, this warming induces feedbacks, a set of physical feedbacks which might lead to more warming, a positive feedback, or which might lead to less warming than a negative feedback. And this is a summary of the most important physical feedbacks. It ranges from Planck feedback. That's basically when you warm a body, it radiates more energy out and therefore provides a very strong negative feedback. You have water vapor, lapse rate, so changes in the vertical structure of the atmosphere lead to a slightly negative feedback. You have the combined of water vapor and lapse rate. You have the clouds and albedo changes. So changes, for example, in surface cover, removing all the trees will change to will lead to a change in albedo. But the key information of that plot is really that the net of all these feedbacks, as estimated by the currently available models, is positive. So all these feedbacks taken together lead to a further warming of the climate system. So the drivers lead to a warming, positive feedback leads to more warming. What you also see from that figure is that for some components, the uncertainties in current set of climate models is actually rather big. And it nicely shows you that the big uncertainty, or one of the big uncertainties in climate models today, is the representation of clouds. That has improved since the force assessment report, but as you can see here, it has by no means been resolved. Same is true for the role of water vapor in these models. Now, if you put this all together, and based on that understanding and the models that we have, and try to look at the last 15 years of temperature record. I've mentioned the temperature over the last 15 years before. here is a figure that shows you 3 plots. One is 1998 to 2012. Red is the observed temperature, right? So we have about 0.05 degrees Celsius warming per decade if you just take the last 15 years. Here is a second 15-year period to compare with. It's 1984 to 1998, just the one before. And there you saw that the warming has been much larger, 0.25 to 0.3 degrees Celsius per decade. And on the right, you have the 1951 to 2012 long-term record, which shows that the overall warming has been about 0.1 degrees Celsius per decade. And plotted on top of this is what the current 40 or 50 available climate models project for these temperature changes. So if they are forced with all we know, this is what the current set of models does. So it's clear that for the 1998 to 2012 period, the models all but one, or kind of one part of this, overestimate the warming that is observed. Interestingly, this is not the case in another 15-year period. So the 15-year before, models tended to underestimate the warming observed over 1984 to 1998. And if you look at the long-term period, the models are actually spot on. They reproduce almost all the exact warming rate over the last 6 years. And what this shows you is that there is a tendency of the models that they are not, that the natural variability in the system cannot be captured 100%. But what they can do, if you look at longer-term records, they really can reproduce long-term trend warming here 60 years, or even the longer-term warming over 100 to 110 years that I've shown at the start. Now, one of the key research questions resulting from the IPCC fifth assessment report and publications shortly before is what causes this difference between models and observations over the last 15 years. And there's a really vastly and quickly growing body of literature looking into this. There is a number of hypotheses out there. One hypothesis is that the actual forcing that the models get, you need to know that the models that we use now, the whole process, how they're forced, how they run, has been set up 10 years ago. So they got their forcing values, and it's obvious that if you look at the radiative forcing from the models and you compare that to the one observed in red again, the models are all over the place. So they don't really well capture. What they get as input is not very well reflecting what actually has been observed over the last 15 years. This, of course, gets better if you look at the long-term period. So one part is, yes, natural variability in the models. Another part is the forcing that the models get. Some people have proposed that actually the deep ocean takes up that heat, and the models are not reflecting that ocean heat uptake accurately enough. But that's really an emerging scientific question, and there have been lots of papers being published. And that's one of the positive outcomes also for the scientific community of such an IPCC report. It really stimulates research because it puts on the table what currently is being considered the status of research, and then people come and actually question that status of research and produce more research, which helps to kind of get a better, more robust understanding. Now, to summarize all this understanding, I go back to the last 60 years of the temperature, and this is the bar for the observed temperature record 1951 to 2010. It's approximately 0.6 to 0.7 degrees Celsius warmed. And using models and statistical analysis in so-called detection attribution studies, scientists try to attribute this warming to different causes. And when they do that, they go through exactly the same drivers that I've discussed before. So they look at CO2, methane, N2O, greenhouse gases, and what they would have as an effect on temperature if there was nothing else but greenhouse gases. They look at aerosols, for example, in yellow. What is the effect of just aerosols on temperature if you exclude all the other components of the sun, of internal natural variability, and here as an additional bar is the total anthropogenic. And what this bar plot shows you nicely is that the actual forcing or the actual temperature change induced from greenhouse gases alone is actually larger than the one that we observe. And this is very much in line with the physical understanding and the radiative forcing bar chart that I showed you. If you put together all the forcings from all the greenhouse gases, we would actually expect more warming. And that's what this analysis really nicely shows. There is the green bar, despite the large uncertainty, goes beyond the actual observed. And we need these aerosols to explain why the bar here, the black bar, is smaller than the green bar. Again, as you could already see from the radiative forcing bar chart, the solar influence on that 60-year temperature change is actually minor compared to the overall anthropogenic influences. And, of course, internal natural variability plays a role. It plays a role if you go to shorter time periods. If you look at 60 or longer time periods, its effect gets smaller. And mostly the external drivers determine the warming. Okay. Summary conclusion for the understanding. We can now go not just temperature, we can do a similar analysis for sea ice, we can do it for ocean heat content, they've tried to do it for precipitation with less confidence. So the overall statement is that human influence on the climate system is clear. Now let's move into the future. And I think I have to speed up a little bit to not go over. When you look at the future, they're dependent on scenarios. These scenarios, as I said, they come from not from physical climate science, they come from economists, from social sciences, they come from technology development, they include population growth, etc. And what IPCC does, or the climate community does, we run these scenarios with the models without deciding whether one scenario is better than the other. We just run them all and then compare them and look at what if this scenario becomes true, what will climate do? And this is what's shown here. This is for temperature. You see the temperature evolution for two scenarios, a so-called RCP 8.5, which you can look at as a business as usual, and then an RCP 2.6, which is a scenario that includes rather strong mitigation actions to keep emissions of greenhouse gases low. Actually, you have to substantially reduce emissions if you want to follow such a path. I think most of the models that try to do this need negative emissions by 2100 if they want to force the climate models to go such a path. And on the right-hand side, you see these bars. They show you the average over 2081 to 2100 for additional scenarios. So there is not just two, there is 4 scenarios that have been run and have been analyzed. And actually the Working Group 3 report will present a much wider range of scenarios. However, roughly the scenarios used by us in Working Group 1 are covering the range of scenarios and potential futures. So based on these analyses, it's likely that the global surface temperature will go above 1.5 degrees Celsius compared to 1850, 1900, which is an analog for pre-industrial in all scenarios, but this lowest. So the probability that we go over 1.5 degrees by 2100 in all the scenarios is more than 66%. Now, if you look at what that means in terms of temperature patterns, and you compare the different scenarios, and here is an early 21st century, so 2016 to 2035 time period, and this is the end of the century. And you can see that it doesn't really matter which scenario you choose or you follow if you look at the next 20, 30, 40 years. So these bars, these maps look very similar, but if you go on the longer term, the scenarios will start to divert, and it's a fundamental difference in the world that we will face if we follow such an RCP 8.5 path, business as usual, or such a strong mitigation scenario, RCP 2.6. Temperature changes, but also cryosphere changes. And one example that might be of relevance for Finland and other Nordic countries is sea ice. What does sea ice cover do, sea ice extent do in the future? And here is an example, the figure that we have in the summary for policymakers. Again, for these two scenarios, the red one and the blue one, business as usual versus strong mitigation. And if you believe these scenarios, and this is just a subset of the scenarios because models are really not doing very well in reproducing Arctic sea ice. So this is only a subset of 5 models here given with the band, which reproduces well the current mean coverage, the trend over the last 30 years, etc. So it's the best models that we have available. These models show that a nearly ice-free Arctic Ocean in September is likely before mid-century for the high-end scenario. That could induce, I mean, that's a potential, but it also bears some danger for the Arctic countries. If you go with the strong mitigation scenario, we might actually never reach such a nearly ice-free stage. The nearly ice-free stage is defined as less than 1 million square kilometers. If you look at sea level, another very policy and impact-related quantity, much more probably than temperature, we see that independent of the scenario, sea level is increasing in the 21st century in all scenarios. It's actually, if you look at, in particular, the business as usual, it's actually speeding up towards the end. And that's one thing which has a long memory. So the sea level is kind of slow in responding to the perturbation from the atmosphere. But it also means that we will see sea level continuing over the next 100 to several hundred years, independent of what choice of scenario we will follow in the future, because of this long-term memory of the ocean temperature and the slow penetration of heat into the deep ocean. So sea level rise projected for 81 to 2000, it's about 26 to 55 centimeters in this lowest of these RCP scenarios. If you look just at the 2100 value, the values are 98 centimeters at the top. Needs to be said that this is again a likely range, so it's only the center 66%. So it's a chance that the actual projections are too high, but there is also a chance that these projections are too low at the end. So it's the central 66% of 100% distribution. Now, I would like to come to the last point, and that's one which we thought is really extremely policy relevant. And it's the link between emissions and temperature change. And what we've tried to do is put that into one, hopefully compelling graph. And the basic message is that the emissions of CO2 largely determine the global mean surface warming by the late 21st century and beyond. And the evidence that we have is that whatever you use, you take the observations, you take models, you take simplified models, all give the same. They give a rather straight, almost linear line if you plot the temperature anomaly versus the emissions in CO2. So a linear relationship. The more emissions of CO2, the higher the warming. And this linear relationship is physically well understood, and it's very robust. If we go and take all the models that are available, all the Earth system models of intermediate complexity, so low reduced complexity models, and even simpler model, we always get the same result. If you go over time, start 1870, and you project over the future, more emissions leads to more warming. A very simple relationship. And what this means is for a policymaker that if you say our target that we want to reach is 2 degrees, we don't want to go over 2 degrees. They can actually go, take that figure and say, okay, 2 degrees, if we just consider CO2 means that if we want to stay with 66% below 2 degrees, we need to limit our total emissions of CO2 to 1,000 gigatons of carbon. That's a physical fact that you can read off this plot. Now, we know all that it's not just CO2, there are other forces, there are other gases, there are aerosols. So if you take the total warming and say, okay, all the components that went into these models and look at what that means, if you want to limit with 66% probability below 2 degrees, the budget is actually reduced to 800 gigatons because there's not just CO2, there's also N2O, which adds to the warming. There's methane that adds to the warming. Yes, we have aerosols that reduce, but aerosols will slowly fade out in the future. So the budget that we have is no longer 1,000 gigatons, it's only 800 gigatons, if you want to limit your temperature to 2 degrees. And also important need to say that this is, to some extent, the non-CO2 part is dependent on the exact setup of the scenario. But that's about roughly the estimated carbon budget that we have available if you want to limit to 2 degrees. You can do the same for a 3-degree target. You can do it for a 1.5-degree target, 4-degree target. That's in the end the policy choice. What physical science can tell you is that there is a budget and it's finite. And if you emit more, Now you will have to reduce more later if you want to stay within these limits. So the conclusion is that limiting climate change will require substantial and sustained reductions of greenhouse gas emissions. And that's one of these statements which are also highlighted in the SPM. So with this, final slides, I've shown you that if you look into the future, we have these scenarios. And one could argue, well, yeah, climate change will happen. We've seen that climate change happens. But if you look at the difference between such an RCP 2.6 and 8.5, it's clear. The choices that we make today, they matter for the future. The question whether these scenarios are feasible and the requirements are not already too high is something that Working Group 1 doesn't look at. This will be discussed by Working Group 3. They will focus on such requirements of these options that we presented. But it's clear that the decision in what kind of a world one wants to live is one which has to be made and living with the consequences. And again, it's not just temperature. More policy relevant probably is if you look at the changes in precipitation. The key conclusion from all the models that we look at and physical understanding is that the dry areas today will get drier in the future under all of the scenarios, much more pronounced in the one in the 8.5 compared to the 2.6. So dry regions become drier and wet regions become wetter. So it's basically telling us that regions that are in need of water supply today will get even in more need for water supply in the future. And with this, I would like to stop and thank you very much for your attention, and once again to the organizers for inviting me to present this report.
Thank you very much, Dr. Plattner. This intergovernmental panel is really a huge undertaking, and we heard about the structure and then about results and scenarios. In this room, we're going to continue later in Finnish, but Dr. Plattner will be available outside for questions. We can still have a few questions here. And I remind you that we are webcasting this, so the mic should be, so that there's a question over there. Just wait a little bit. And a short question, no lecture.
Okay.
Please.
Now, one critical test for your models is how well have they described the past. The last issue of Nature had an article on this, and over the last 15 years, the models give an average increase per decade of 0.21 degrees. The actual is 0.04. Now, in any other kind of science, when you sort of are 5 times off the target, it would be rubbish. What do you say to that?
Well, I would say that I think I've actually hopefully compellingly covered that topic. There was this figure in the understanding plot which actually shows exactly this, that the observed warming is substantially lower than what the models do. Now you need to understand that these models are trying to reproduce, so they are forced and started in 1850. And as I said, there is a lot of science going into improving the representation of natural variability in these. The fact that the models don't reproduce that warming over the last 15 years is a fact that is clear. It's clearly stated in the IPCC report. It's also clear that nobody has here is the answer. I understand why. There's lots of hypotheses out there. And it's also a fact that papers like the one that you cited, and actually many papers that have been published on that particular topic, came out after the cutoff date for papers being included in the report. You need to understand that in the IPCC report, we have a fixed deadline, which was March 15, 2013, and papers published or accepted after that deadline can no longer be included, because if we would do that, we would never give the expert reviewers and the governments a chance to actually to put that out and look at what these papers said. I would say I fully agree. The models do have a problem. I would say that I think models are not doing climate predictions. So I don't expect the models to do a year-by-year variability. I also don't expect them to do a 5 to 10 year variability to 100%. But overall, I think we all agree, if you look at the long-term trend, they do extremely well. If we do at shorter-term trends, there is an underestimate of variability, and it's hopefully a scientific questions that we can resolve with more years to come of observed records, because that's going to be an interesting question. What happens to that pause or hiatus? And B, is it really a flaw in the models, or is it a flaw in the forcings that drive the models, or something else? So it's a very active area of research, and I know that there's actually several papers coming out on exactly that topic with different hypotheses. So far, no agreement on what the cause is. I wouldn't call it rubbish, though.
Possible quick question? If not, then thank you, Dr. Plattner.
Thank you very much.